Good morning, friends. In previous lecture, we have seen air standard cycle of gas turbine power plant, thermal efficiency of gas turbine power plant, ideal and actual thermal efficiency of gas turbine power plant. Today, we will discuss Brayton cycle with regeneration. Here, in gas turbine engine, the temperature of the exhaust gas leaving the turbine is often considerably higher than the temperature of air leaving the compressor. Therefore, the high pressure air leaving the compressor can be heated by the hot exhaust gases in counterflow heat exchanger, regeneration, recuperator. The thermal efficiency of Brayton cycle increases as a result of regeneration since less fuel is used for the same work output. We can show figure here Brayton gas turbine engine with regenerator. Here air in from atmosphere to the compressor, from compressor to the combustion chamber, and combustion chamber to turbine, and turbine exhaust gases reheated in the regeneration process and used for the compressor. Here exhaust gases give the heat to compressor output gases. Heat transfer from exhaust gases to combustion chamber inlet gases. That's why we here increase efficiency of the plant. Here figure shows TS diagram of gas turbine engine with regenerator. Q regeneration actual H5 minus H2. Q maximum equal to H5 minus H2 equal to H4 minus H2. Effectiveness equal to H5 minus H2 upon H4 minus H2. Effectiveness approximately equal to H5 minus H2 upon H4 upon minus H2. TH diagram of Brayton cycle with regeneration we can show here. The thermal efficiency depends on the ratio of the minimum to maximum temperature as well as the pressure ratio. Regeneration is most effective at low pressure ratio and low minimum to maximum temperature ratio. Can regeneration be used at high pressure ratio? Thermal efficiency of the ideal Brayton cycle with and without regeneration. Thermal efficiency with regeneration 1 minus T1 upon T3 into pressure ratio raised to K minus 1 upon K under cold air standard assumption. Here in this graph shows Brayton thermal efficiency versus pressure ratio with generation and without regeneration. After that, example on regeneration for assignment. Solve this example. A Brayton cycle with regeneration using air as the working fluid has a pressure ratio of 7. The minimum and maximum temperature in cycle are 310 and 1150 Kelvin. Assume an isentropic efficiency of 75% for the compressor and 82% for the turbine, and an effectiveness of 65% for the regenerator. Determine A. The air temperature at the turbine exit. B. The net work output. C. The thermal efficiency. The Brayton cycle with intercooling, reheating and regeneration. For minimizing work input to compressor and maximizing work output for turbine, Figure shows a gas turbine engine with two-stage compression with intercooling, two-stage expansion with reheating, the regeneration and its TS diagram. Here, air coming from atmosphere to compressor. In compressor first and second compressor, intercooler is connected. In between intercooler are connected. After that air goes to the combustion chamber through regenerator. From combustion chamber to turbine, turbine to reheater, reheater to turbine second, and turbine second to exhaust gases from through regenerator. Figure shows TS diagram of gas turbine engine with two-stage compression with intercooling, two-stage expansion with reheating and regeneration, and TS diagram. Multi-stage compression and with intercooling. The work required to compress a gas between two specified pressure can be decreased by carrying out the compression process in stage and cooling the gas in between. This keeps the specific volume at low as possible. Multi-stage expansion with reheating keep the specific volume of the working fluid as high as possible during the expansion process, thus maximizing the work output. Intercooling and reheating always decrease the thermal efficiency unless they are accommodated by regeneration. A number of compression and expansion stages increase the gas turbine cycle with intercooling, reheating, regeneration approaches the Ericsson cycle. Here, graph shows thermal efficiency versus pressure ratio. Thermal efficiency versus pressure ratio in reheat and simper. In this graph, difference between reheat and simper curve shown in thermal efficiency and pressure versus pressure ratio graph. In this graph, regenerative and simper, difference between regenerative process and simper process. Here shows the remitting turbine inlet temperature, thermal efficiency versus pressure ratio, effect of pressure ratio and turbine inlet temperature. Graph shows effect of thermal pressure ratio and turbine inlet temperature. Effect of compression inlet temperature, thermal efficiency versus pressure ratio. Example 3, an ideal gas turbine cycle with two stages of compression and two stages of expansion has an overall pressure ratio of 8. Air enters each stage of the compressor at 300 Kelvin and each stage of the turbine at 1300 Kelvin. Determine the back work ratio and thermal efficiency of this gas turbine cycle assuming A. Not regenerator. Assuming A. No regenerator. B. An ideal regenerator with 100% effectiveness. Compare the result with those obtained in example 1. Thank you. Here we have complete 4th unit gas power plant. Next lecture we will discuss 5th unit. Thank you.